Welcome back, everybody, to our discussion of solutions. And we have talked about what a solution is and what a solvent is and a solute. And we talked about characterizing solutions into saturated, unsaturated, and supersaturated. And we've talked about characterizing solutes and saying, hey, they can be electrolytes or weak electrolytes or non-electrolytes. And so now I want to go in a slightly different direction, and we want to talk a little bit about factors which affect solubility. So let us read this consider here. Consider methane and ammonia. First thing we want to do is draw the Lewis structures for each. Okay, I can do that. Methane, right? That's going to be CH4. I'm going to put C in the middle. Oh, first thing I have to do is count my valence electrons. I get 4 out of carbon, 1 out of hydrogen 4 times, so I have 8 valence electrons. Write my central atom, surround it with the others, and bond it, and then count my complete octets, but we know hydrogen only wants 2 electrons, and then count 2, 4, 6, 8, so I have 8 valence electrons. That's the picture. Beautiful. Ammonia, NH3, this is a fiver, and 1 times 3, that's 8. Nitrogen in the middle, we're going to put some hydrogens here. Good. And let's count 2, 4, 6. Hey, I'm missing 2 electrons on my nitrogen. Have to complete that octet. 2, 4, 6, 8. Good. There we go. So that's my picture of my ammonia. By the way, what is the shape over here of this puppy? That is what? Well, that is, looks to me like tetrahedral. Okay, now tetrahedral, that is what? That is a symmetric shape, and I have the same atoms around it. So would you all agree that this is non-polar? Yes, I'd say it's non-polar. If it's non-polar, what kind of ion forces does it have? Well, can it have hydrogen bonding? No, it's got to be polar to have hydrogen bonding. And it's got to be hydrogen between hydrogen and not carbon, but oxygen, nitrogen, and fluorine. So that's not hydrogen bonding. Does it have dipole-dipole? No, it only has London dispersion. Good. What do I have over here? That looks to me like what? It's a 3-1 situation. This was a 4-0, right? 3-1, that would be trigonal pyramidal or pyramidal, right? Good, yeah. All right, is that polar? Well, trigonal pyramidal is asymmetric. That means it's going to be polar. Good. If it's polar, it has London and dipole. Now, what else? Well, I have, if we look at this, let's draw 2 of them just to get a nice picture of this, right? Let's do it this way. I'd have hydrogen, 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 and unshared, and here's my nitrogen, hydrogen, 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 and an unshared, right? And what do we get here between this hydrogen and this unshared? Okay, I have a nitrogen here, so I have a nitrogen-hydrogen bond, and I have an unshared pair of electrons. And what do we get between that hydrogen and that unshared pair? That is what we call our hydrogen bonding. Cool. So I have London dispersion, dipole, and hydrogen bonding. Cool. And if you don't remember that, go back and take a look at our discussion on uh, intermolecular forces. Perfect. So that's kind of the background. Now I've drawn my Lewis structures. Which is more soluble in water? Which is more soluble in water? All right. I think we need to run back and make some more notes. We go back to our beautiful note sheet, and let's run another line off of solutions. And we're going to go down this left side. Na 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 na. Holy moly. Whoo! Finally, let's write down factors affecting solubility. Factors affecting solubility. And the first thing we need to know is, what is solubility? Well, solubility, and we're going to kind of simplify this, but it's essentially the amount of solute which dissolves. Okay, that's a rough definition of solubility. The amount of solute which dissolves really before forming a saturated solution. But we can think of it as the amount of solute which dissolves. How much solute will dissolve? Okay, now there are three factors that we want to talk about. One, the first is the solute-solvent nature. The nature of the solute solvent. And what this is this is based on IM forces. And what we mean here is when my solute and solvent have similar IM forces, then the solubility tends to increase. Okay, now let me give you a nice little substitute for that. We just simply say likes dissolve likes. And if you remember that, that is sufficient. And what does that mean? Substances with similar IM forces dissolve in each other. And maybe we should clarify this a little bit. When we say that, we really mean, hey, London forces will dissolve in things that have London forces. Dipole hydrogen tend to dissolve in things that have dipole or hydrogen. Okay? And one other thing, ionic usually will dissolve in dipole substances or substances that have hydrogen bonding. And that is why sodium chloride, which is ionic, will dissolve in water. Why? Well, water has hydrogen bonding, and so it's relatively strong, and so even though this is ionic, it will dissolve in the water. But the general rule of thumb for us is simply likes dissolve likes. If you have something that only has London, it will not dissolve in something that has hydrogen bonds, and so forth. Okay? Good. That's number one. Let's take a look. Can we answer our question? So, which of these is more soluble in water? Well, let's look at water. What kind of IM forces does water have? If we draw our picture of water, I have oxygen with a hydrogen and a hydrogen. I've got two unshared pairs. We say, hey, man, that is what? 2-2. It's a bent shape. That means it is asymmetric. And if it's asymmetric, it's going to be polar. And if it's polar, it's certainly going to have London and dipole. Not only that, it has a hydrogen bonded to an oxygen and an unshared pair, so it has hydrogen bonding. So, which of these, methane, which only has London forces, and ammonia, which has hydrogen bonding, among others, which of these is more likely to dissolve in water? Well, water has hydrogen bonding, ammonia has hydrogen bonding, so it's more likely that ammonia will dissolve in water. Cool, that's not hard. You guys do this one. Bring me back when you're ready. Well, I have water and methane. Water looks like this, right? We just established that it has dipole, London, and hydrogen bonding. We already established that methane was tetrahedral, and so it only had London forces. Now, butane. What does this butane look like? It looks like this, right? Yoink, 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 yoink. Bunch of hydrogens around here. Good. Does that look like it is symmetric? Or does it look like it's non-symmetric? Well, actually, it is symmetric. That means it is non-polar, because not only is it symmetric, but everything around my carbons are exactly the same. So it's nonpolar. If it's nonpolar, it only has London forces. So which of these is most likely to dissolve in it? Water, which has, among other things, hydrogen bonding, or methane, which only has London. Well, these guys have like. They're both alike, so the answer is methane is more likely to dissolve in, to be more soluble in butane than water. Got it? Cool. Moving on. Next. Oops. There we go. Consider calcium fluoride and water. At 25 Celsius in 1 atmosphere, I have 0.016 gram of calcium fluoride, and that's how much will dissolve in 1 liter. Okay, so that's my solubility. Will more or less dissolve when the temperature of the water is raised. Okay, so I have a solid dissolving in water, and we want to look at the effect of temp. All right, let's go back to our notes. Here are our notes. Let's go way down here, and we want to look at another effect. And this is going to be the effect of temp. And here is our general rule. The effect of temperature, and we're gonna limit our discussion to the effect of temperature when water is solvent. So we just want to talk about water being the solvent and what happens when we change temp. Number one, the effect of temperature. The solubility of solids and liquids in water increases with increasing temp. So as my temperature increases, the solubility of my solids and liquids in water increases. Good. However, well, we'll leave it right there. So let's go back to our question here and look at our answer. There we go. What happens? The temperature of the water is raised. So when the temp is raised, solids and liquids increase their solubility. So what would I say will more or less dissolve? The answer is more will dissolve. Will more or less dissolve, let's go to the next question, will more or less dissolve when the pressure is doubled? Ooh, we're really going to increase pressure, aren't we? So let's talk about pressure effects. Solubility, okay. Number 2, let's go down here, pressure. The solubility, oops, I guess I should, yeah, there's temp. What's the effect of temp? Let's come over here. I need to draw another line. Get rid of number 2. Let's take this down farther. Sorry, I got to keep my beautiful concept map going. What's the effect of pressure? 1. Pressure has little impact on the solubility of solids and liquids in water. So it really doesn't matter. If I double my pressure, it's really going to have no major impact. So it won't matter. Why? Because I have a solid in water and the pressure just doesn't have an impact. Doesn't matter. No change. No significant change. Okay? All right. Here you go. So here's the next one for you to do, and this will be our last one of the day, so let's get it right. Consider gaseous oxygen and water at 20 Celsius and 1 atmosphere, 7.6 times 10 to the minus third grams of oxygen will dissolve in 1 liter of water. Will more or less dissolve when the temp is raised. Okay, you guys try to figure this out, and I'll come back with an answer. Will more or less dissolve when the pressure is doubled? Okay, you ready? Cool. Well, what did we say about gases in our notes? Let's go back up and look. What did we say about gases in our notes? Yoink. We said temperature. Here's our temperature effect. The solubility of solids and liquids in water will increase with increasing temp. What did we say about gas? We said nothing about gas because there's a different rule about gases. The solubility, beautiful, of gases in water decreases with increasing temp. So as the temp increases, you get less solubility. The water will hold less oxygen. And so I was really kind of setting you up. This is kind of a trick question, right? Because I didn't give you the notes yet. I have gaseous oxygen and water. What am I going to go do to my temp? My temp is going to be raised. So temp goes up. What happens to the solubility of a gas? The solubility of the gas goes down. Good. Let's go back and look at our notes on solubility of gases with pressure. And if you're sharp cookies, and by what is a sharp cookie? I can understand sharp knives. I don't understand sharp cookies. Maybe you're a tough cookie. So if you're a tough cookie, we'd have figured this out. That we didn't have any rules on pressure related to gas. The solubility of gases in water increases with increasing pressure. So the greater the pressure over my liquid, the greater the over my water, the greater the solubility of the gas. Okay? And so we can answer that question now. What happens with more or less dissolve when pressure is doubled? Pressure is doubled. We're talking about a gas. So if my pressure is doubled and my gas is over my water, what's going to happen? More will dissolve. So when pressure increases, solubility of my gas in water increases. Good. All right. There you go. So we've covered another topic. This should be good for today. Next time, we're going to get into how we can characterize the amount of solute in the solvent, which we call concentration. And we'll get into the concept of molarity. And then, man, guess what's coming up? Ooh, solution stoichiometry. You just cannot get enough of stoichiometry, can we? So next time we'll get into molarity, and then after that stoichiometry. But for today, that will be it. You have now mastered the basics of solutions. See you next time.